Alright, hi everyone and welcome back to this channel. So in the previous video we did the MCQs related to the chapter of momentum. Now we're doing structured questions. Also I must point out a typo in the previous video. It just said IGCSE here for the MCQ section, but it's basically MCQs relevant to us from both the IGCSE and O-level boards. And similarly we're doing something same here. So we're also looking at actual past paper questions and then other questions that I've got from the specimen paper and whatnot. Again, because I've selected this and I've handpicked these questions, it means all of these are relevant for you and all of these will be a huge help while preparing for your tests. Alright, question number 1. So this is the reference from the O-levels. A spacecraft of mass 300 kg is moving in a straight line at a speed of 8,000 meters per second. Calculate the momentum of the spacecraft. Some of you might know the formula. Actually, you obviously should know the formula. But don't be so quick to just multiply and write this here, because this is a 2-mark question. There's 1 mark for the working. So showing that this is the formula. Mass is 300. The speed and hence the velocity is 8,000 meters per second. So this turns out to be kg meters per second. One of those parts where the units are already given, so you don't need to do anything much. Next, fuel on the spacecraft explodes and the spacecraft splits into 2 parts. The direction in which the parts move do not change. Let me zoom in here a bit more. So it has a mass. After the explosion, the speed of the front part increases to 900 meters per second. It has a mass of 150 kg. Calculate the speed of the rear part after the explosion. So initially the total mass of the spacecraft was 300 kg and this was initially moving at 8,000 meters per second, corresponding to which we found its initial momentum. And then it splits into 2 parts, and obviously if the mass of one part is 150, the mass of the other part must also be 150 by 300 minus 150, and we need to find the speed of the rear part after the explosion. So total momentum before, actually this is a paper 2 question, it's better if you write it out completely. Total momentum before equals total momentum after. So total momentum before I have already, which is this, the answer to my previous part, equals total momentum after. So the speed of the front part, and it's moving in the same direction. So it's 150 mass times its velocity 9,000. And I need to find for the rear part, so that's 150 times v. So I just need to solve this equation and I need to find v. So from this, v turns out to be 7,000 meters per second. Again, this is a trend with the newer questions that you already have the units and you do not have to write that, which I guess you would agree as well, that is pretty good for you guys. Total kinetic energy of the 2 parts after the explosion is greater than the original kinetic energy of the spacecraft, right? So initially the kinetic energy was less, and afterwards it's greater. So this means that energy must have been transferred from some store into the kinetic energy. And the hint here lies with this word. Fuel is basically a store of chemical potential energy. So the idea is here. So the idea here is this, that chemical potential energy is transferred to kinetic energy. That's why the kinetic energy is greater after. Explosion lasts for 2 seconds. Calculate the average force on the front part during this time. So force is rate of change of momentum. I need the change in momentum for just the front part. So that's final minus initial over time. Final would be mv minus mu over delta t. And you know I can factor out this. I'm just doing this again just in case you've had quite a long break between watching the previous video and this video. So mass of the front part, or the rear part for that matter, was 150. Final velocity of the front part is 9,000. Initially it was 8,000 because initially they were both together. So 9,000 minus 8,000, and the time is 0.2 seconds. So this gives me 750,000, which I can also write in standard form as 7.5 into 10 to the 5. Going on, question number 2, this is its reference, another Winter 23 paper. Both of these were Winter 23, just different variants. 1.1 shows a toy water rocket. Rocket is half filled with water and connected by rubber tubing to a pump. Air is pumped into the rocket so that the pressure of the air inside the rocket increases. Explain in terms of particles why the air in the rocket exerts a pressure on the walls of the rocket. A lot of people misunderstand questions like these and they try to somehow link it with temperature or volume. This is not what is asked in this question. All you need to explain is why would the air in the rocket even exert a pressure in the first place. And you always go about responding to this question in the same manner. You say this, that the air particles, in this case, otherwise you would just say particles, are in constant random motion. Then we say this, that they collide with the walls of the container. This is your second mark basically, and this exerts a force which leads to a pressure. Alright, so that's the answer to this first one, which was not really linked to momentum here. Temperature of air in the rocket remains constant as air is pumped into the rocket. Explain why increasing the number of air particles increases the pressure. So if you have more number of air particles, how would that apply a greater force? And you just need to say this here, that you'll have more frequent collisions which would obviously exert a greater average force, leading to a higher pressure. Instead of more frequent collisions, you can also say more collisions per unit time. Both of these are correct. Alright. When the air pressure in the rocket is high, the rubber tubing is removed from the rocket. Water in the rocket is expelled downwards. Explain in terms of momentum why the rocket begins to accelerate upwards. Now, here we know that when this tubing is going to be removed, water will be expelled downwards. Hence, water has a downwards momentum. And because of this water being expelled downwards, it would have a downwards momentum. And total momentum before was 0, which also means that by the conservation of momentum, total momentum after must also be 0. So if the water has a downwards momentum, the rocket must have an upwards momentum, so that it's equal and opposite momentums for both momenta. To be more specific, momenta is plural of momentum, and that's how they would cancel out. Now this is basically what I'll be writing for as a response to this question. So this is my response. The water has momentum downwards by conservation of momentum. The rocket must have the same amount of momentum but upwards. And because the rocket experiences a change in momentum by the definition of force, there's a rate of change of momentum here, which is going to cause a force leading to acceleration. Alright. As the water is expelled from the rocket, upward acceleration of the rocket changes. Suggest two reasons for the change in acceleration of the rocket. Now again, a suggest part, students of mine know that I talk a lot about these because this is the most difficult part of O-level physics paper 2 questions, because you have to really think about these. Now one reason here is obvious, is that for this rocket, because water is going to keep on being lost downwards, so the mass of the rocket would change, and that would cause the acceleration to change as well. So the first thing I would say is this: the mass of the rocket decreases because of the water. So that's the first one. And as the rocket accelerates, its speed would increase, and we know of a certain force which would also increase as a result, and that's air resistance. Apart from this, the examiner also accepted something like this, that as the water is being expelled, less water is expelled per second. It's expelled at a lesser rate, so that's why the acceleration changes. You can also talk about gravitational field strength. You know that decreases with height, so because of that also the acceleration could change. Let's go on to the next question. Alright, so this graph shows a speed time graph for a car traveling on a straight horizontal road. It's a speed time graph. So first step, speed time. Next step, gradient is acceleration. And area under this graph is distance. Now we'll start. Describe the motion of the car shown in 1.1. So first of all, till 10 seconds, I can see this is constant speed. And after this, the speed is decreasing, but this is not a line, right? So how would I talk about this? Again, I can use this idea that gradient is acceleration. And because this is not a straight line, the gradient is not constant, so the acceleration is not constant. Even if you said this, the examiner would give you marks, but I'm not happy with this. I want just a bit more of a detailed explanation. Let's say if I find the gradient at this point, then it's going to look like this. Versus if I find the gradient at this point, this looks like this. This means that initially the speed was decreasing more because the gradient here is steeper, and then it's not as steep. So I would say this is a case where it's first decelerating faster, then it's not decreasing, then it's not decelerating as fast. So this is a case of decreasing deceleration. Also, just by the way, decreasing and increasing deceleration is not part of the O-level or the IGCSE syllabus, but increasing and decreasing acceleration are part of your syllabus. At time t equals to 10 seconds, the engine of the car is switched off, brakes are not applied. Name two forces acting on the car that cause the change in motion. Now, because of the change in motion, I know that if this is going on a horizontal road, the weight is a force that acts, but it would not cause a change in motion. So one thing I can say is obviously something like air resistance, right? And the other one would just be the friction with the road. So friction between the tires of the car and the road, right? Suggest, again, a suggest part. Suggest why 1.1 is a curve after t equals to 10 seconds. This is also pretty easy to understand, is because if you know that it was slowing down here, you know that the air resistance is going to decrease. So you can just say that air resistance decreases as speed decreases. So that's what you had to say here. Next part. Between 10 and 20 seconds, the speed of the car changes from 18 to 11. Mass of the car is given. Find the change in momentum of the car. Give the unit of your answer. For units, you can either write Newton second or kg meter per second. There's no such preference. Change in momentum is mv minus mu. You can factor out the m, which is 1200. Final speed is 11. Initial speed is 18. So this turns out to be negative 8400. If you write the negative or not, it doesn't make a difference because it's just asking about change anyway. Calculate the average resultant force exerted on the car during this time. So you just found the change in momentum. You can just use the definition of force, which is 8400, and the force, this happened during a time of 10 to 20. So 20 minus 10 is 10 seconds, which is going to be 840 newtons. Again, the unit is written for me. Let's go on to the next question. Question number 4. So in a safety test, a car of mass 1100 kg is traveling at a speed of 10, collides with a stationary mass of 3000 kg. After the collision, the car and the van move together, so they stick with a velocity v. 2.1 shows the car and van before and after. Total momentum is conserved. We know this for a fact. Define momentum, simply the product of mass and velocity. Next part, state the unit of momentum. Again, kg meter per second or Newton second, both are correct. Calculate the velocity of the car and van after the collision. I know for a fact that because this is 2 marks, this is not what the examiner would give marks for, but I'm still going to write it. Just to establish this as a habit, so that wherever marks are there, I'm hardwired to write this there as well. So total momentum before equals total momentum after. Before, it's 1100 times 10 and none for the van, so 1100 times 10. If you want to write this, you can. If you don't want to, that's also fine. Afterwards they stick, so the combined mass is 3000 plus 1100, which is 4100, and this is its velocity after. Now I just need to find this out. So this turns out to be 2.6829. You can write 2.68 correct to 3SF or 2.7 correct to 2SF. Calculate total kinetic energy of car and van after the collision. So kinetic energy is half mv squared. So half mass of the combined object was 4100, and this is the speed 2.68 squared. To avoid rounding errors, you should use whatever calculator value that you have here, which turns out to be 14,756, or I can say 1.48 into 10 to the 4 joules. State the transfer of energy that occurs in the collision. So we know that here there has been some kinetic energy initially, and then they have some kinetic energy after as well. So there must have been some energy lost. So I would say that kinetic energy to thermal energy of collision, or I could have also said this, and the examiner was willing to accept this, is basically that the kinetic energy of just the car becomes the kinetic energy of the van and the car, right? So you can also talk about this. Let's go on to the next question. Question number 5. Now these are IGCSE questions, the one that have the references missing. Let's start with this question. 3.1 shows water flowing at a very slow speed over a cliff edge. The water falls 15 meters onto the rocks below. Show the velocity of the water when it strikes the rocks is 17 meters per second. Now I guess it's not very obvious, but you need to think what this means and what would happen as it falls over the cliff edge, which is 15 meters high. So the idea is that it would lose its gravitational potential energy, and in turn it would gain kinetic energy. When it's saying it flows at a very slow speed, this is basically your cue that initially you can say the kinetic energy was 0. So the speed is almost 0, so the kinetic energy is almost 0. So then you need to show that the velocity of the water when it strikes the rock is 17 meters per second. Again, what you would say is this, that the loss in potential energy equals the gain in kinetic energy. You might see that there is no mass provided to you for the water, and that's for a reason. So writing this as mgh equals to half mv square, you'll see that the m's cancel out anyway. So this means that the mass of the water does not have any effect on the speed of the water. And then you need to find v, which in symbols is just root 2gh, which is root 2 into g, which is 9.8, and the height from which it falls is 15, and this turns out to be, so this is root of 294, which turns out to be 17.1 or 17 meters per second, correct to 2SF. So this is part 1. Part B says 30 kg of water flows over the cliff edge every second. Calculate the force exerted by the rocks on the falling water. Ignore any splashing. So for finding the force, I can use this idea that this is the rate of change of momentum. So I can say that the change in momentum would be final minus initial over the time that it takes. Now, final momentum I would say is 0 because the examiner says ignore any splashing. So basically I would assume that all the water, when it hits the rock, it comes to rest. So finally there is no momentum. Initially the momentum I can find, this is the mass and this is the speed with which it hits. So that's the velocity, and divided by the time, because this is per second, this time is basically 1 second. So 30 times 17 is basically the value for my force, which turns out to be 510, and this would be in newtons. Again, I hope you guys understand here that I actually use whatever calculator value that I got into this equation, and that also turned out to be 510 Newton to 2SF. So this is what you should do to avoid rounding errors. Let's go on to the next question. 2.1 shows a wooden trolley of mass 1.2 kg at rest on the rough surface of a bench. Ball of mass 0.52 grams travels horizontally towards the trolley. Ball embeds itself in the wood of the trolley. Trolley moves with an initial speed of this much. Find the impulse exerted on the trolley. So impulse is basically delta P, the change in momentum. We know these two formulas, F delta T or final minus initial momentum. I have no force, I have no time, so I'll need to use final minus initial momentum. I know the mass of the trolley is 1.2, so mass times final velocity. Finally it moves with this, and there was no initial, so it's basically this. So this value turns out to be 0.078. So you can write this as Newton second or also as kg meters per second. Both are correct units. Next part, the speed of the ball as it hits the trolley. So how do we find the speed of the ball as it hits the trolley? For this, we basically have to use the conservation of momentum. We need to find the speed of the ball before, and this is the trolley, and then the ball embeds itself in the trolley and then they move off together. So I would use this, that total initial momentum equals total final momentum. So total momentum before collision equals total momentum after. So this is the ball which has a mass of 0.52 grams. So this is 0.52, and if I look at the other one is in kg, so I will need to convert any one of them. Let's say I choose to convert the grams to kg. So 0.52 over 1000 multiplied by its speed, this is what I need to find. And after the collision, I know that it moves with this speed. Since this is a case of a sticky collision, I know the masses would be added up. So that's 1.2 kg plus 0.52 grams, which would make this. Now again, I would be converting the mass to kg because this one as well I converted to kg. So 1.2 kg plus 0.52 over 1000. This turns out to be, again, it's a pretty weird value, 1.20052 times its speed, which is 0.065. And using this, you just find V. So you just cross multiply here and here. So this turns out to be 150.065, which is basically 150 meters per second. Also, the examiner gave these values on purpose because you know that 1.2 kg plus 0.52 grams, so the 0.52 doesn't really make a lot of difference. So in this case, if you also assumed it like this, that it's just 1.2 before as well as after, your answer would still be fairly close, right? So this is the answer that we get. As the trolley moves across the rough surface, it slows down and stops. Explain in terms of work done the energy change that takes place as the trolley slows down. So we know that as it's slowing down, we would say there is a loss in kinetic energy, and we also know the reason for this. So there is a loss in kinetic energy because of work done by friction on trolley, right? The friction takes away energy from the trolley, producing thermal or internal energy. Right, so that's all you need to say here. Let's go on to the next question. Question number 7. Complete the definitions by giving the name of each quantity. Mass times acceleration is resultant force. Force times time is impulse, or you can also say the change in momentum. 2.2 shows a man using a golf club to hit a ball. The ball has a mass of 0.046 kg. Golf club is in contact for a duration of this much, leaves at a speed of this much. Calculate the momentum of the golf ball as it leaves. Very easy. Just P equals to mv. So 0.046 times 65 turns out to be 2.99 exactly. Again, units are missing, so kg meter per second or Newton second. Or if you were to write this to 2SF, which I'm pretty sure is what would have been done in the mark scheme, this would be 3.0 kg meters per second. Average resultant force, using the definition of force, I got the change in momentum from the previous part. The time in contact is given over 5.0 into 10 to the negative 4, and you find the force, which is 5980. Again, this is a force, so this is newtons. When the golf club is in contact with the ball becomes compressed and changes shape. State the type of energy stored in the ball during its contact. So we know that in such cases when something is deformed, it stores elastic potential energy. Let's go on to the next question. The velocity of an object of mass m increases from u to v. State in terms of mu and v change of momentum. So final, mass times final, minus mass times initial. This is the change. In a game of tennis, a player hits a stationary ball with his racket. Racket is in contact for 6 milliseconds. Average force is given. Find the impulse. So impulse is F delta t. F is 400. This is time, which is in milliseconds. So milli is 10 to the negative 3. So this turns out to be 2.4. Again, this is the same units as momentum. So Newton second or kg meters per second. Mass of the ball is given. Calculate the speed with which the ball leaves the racket. So I know that the impulse, because initially the ball was stationary, so the impulse, which is just the change in momentum, that's really the final momentum, right? Because usually I would say final minus initial, but there is nothing here, so it's minus 0. So that is equal to 2.4, which I know is mv, so 0.056 times v, and you find out v from here. So v turns out to be 42.857, so 42.9 or 43 meters per second are both correct. State the energy transfer that takes place as the ball changes shape during the contact between the racket and the ball. In that case, so the moving racket, which would basically have kinetic energy, that changes the shape of the ball. Hence, I would say that the kinetic energy of the racket is transferred to the elastic potential energy of the ball, right? And then as the ball leaves the racket, so the elastic potential energy of the ball turns into the kinetic energy of the ball, right? Because after it undergoes this change in shape, after that it starts moving. Let's go on to the next question. Question number 9. 2.1 is a top view of a small ship of mass this much. Ship is moving slowly sideways at 0.040 meters per second as it comes into dock. This is shown. Ship hits the wooden pillars which move towards the dock wall. Calculate kinetic energy of ship before it hits the pillars. So half mv square. Mass is 1.2 into 10 to the 6, and the speed was 0.040. This would be squared, and you just find this out. So this turns out to be 960 joules. The ship is in contact with the pillars for 0.3 seconds as it comes to rest. Find the average force exerted on the side of the ship. Again, force is the rate of change of momentum. So Pf minus Pi over delta t, or mv minus mu over delta t. Obviously final momentum is 0 because it comes to rest. So 0 minus mass, which is 1.2 into 10 to the 6, into its initial velocity, which is 0.040, divided by the time, which is 0.3 seconds. So you find this out. So this value for the force turns out to be 1.6 into 10 to the 5 newtons. Next, assume kinetic energy is used to do work moving the pillars. Calculate the distance moved by the pillars. So I found the kinetic energy, and this was the force exerted on the side of the ship by the pillars. By Newton's third law, this would also be the force exerted by the ship on the pillars. So this is what you need to use in the next part. So this is the energy which is transferred, 960. This is the work done to move the pillars, which would be force into distance. So force is 1.6 into 10 to the 5, force times the distance. And from here, I need to find the distance. So this turns out to be 6.0 into 10 to the negative 3 meters. Dock walls sometimes have the pillars replaced with rubber car tires. Explain how this reduces the possibility of damage when a boat docks. This is actually a good question because you know that with the rubber car tires, you would say the time in contact, I can say the time for the boat to come to rest. Increases, and by this formula I know that if time goes up, the force acting would go down, so which causes a lesser force on the boat, right? So which reduces damage, obviously. Let's go on to the next one. Question 10. A rocket is stationary on the launch pad at time t equals to 0. Rocket engine is switched on. Exhaust gases are ejected. Rocket accelerates upwards. 1.1 shows how acceleration varies between this and this. So you see the acceleration is increasing, then acceleration becomes constant, right? So this is kind of an unconventional question because acceleration time graphs are usually not part of your syllabus. Define acceleration, pretty easy. Rate of change of velocity, or the other only possible correct definition is change in velocity over change in time. Everything else depends on the examiner's mood. Maybe he might accept change in velocity per unit time some days, other days maybe he won't accept it. Sketch a graph to show how the speed of the rocket varies between time t equals to 0 and time t equals to t f. So the idea is just that here the acceleration is increasing, which means that if I'm talking about a speed time graph, I know the gradient of this is acceleration. So if the gradient is acceleration, I know that at first it's going to increase, whatever this first stage was, because the acceleration was increasing, so the gradient is also going to increase. Then the acceleration becomes constant, which means the gradient becomes constant. Then it would just become a straight line. So this is corresponding to both of these stages, which was shown in the graph above as well. Alright, these are the later two parts. Sometime later, the rocket is far from Earth. Effect of Earth's gravity is insignificant. As the rocket accelerates, its momentum increases. State the principle of conservation of momentum. Very easy, which is this: for a closed system or an isolated system, or you might say no external forces acting, total momentum before equals total momentum after collision. Or you can also say that the total momentum remains constant. That's also fine. Explain how the principle of the conservation of momentum applies to the accelerating rocket and the exhaust gases. So you know that, for example, if I'm talking about the rocket going, so it's expelling gases. So I would say that the gases have momentum in some direction, Then I would say this, that for momentum to be conserved, so for conservation of momentum, I would say the rocket has equal and opposite, the rocket has equal momentum in the opposite direction as the gas. In opposite direction to gas. I'm pretty sure this is just what the examiner asks, but for completeness, I'm also going to talk about what it means for it to be accelerating. And acceleration is basically linked to resultant force. So I would say, since there is a rate of change of momentum, or you can also just say, since there is a change in momentum, a resultant force acts, causing acceleration. Right, so that's the answer to this part. Let's go on to the next question. So part A, underline pair of quantities which must be multiplied together to calculate impulse. So we know impulse is this delta P, which is F delta T, so force and time, which is this thing right here. Part B, 3.1 shows a collision between two blocks A and B on a smooth horizontal surface. Before collision, A of mass 2.4 kg is moving at 3 meters per second. B is at rest. After collision, blocks A and B stick together and move with velocity v. Calculate momentum of block A before collision. So this is very easy. It's just mv. So 2.4 times 3, which is 7.2 kg meters per second. Next part, the velocity v of the combined object. So for this, you'll need to use the conservation of momentum. So total momentum before collision equals total momentum after. So I would say, I've already actually found the total momentum before. So 7.2 equals total momentum after. Because this is a sticky collision, their masses would be added, equals to 3.6 times its velocity, v. And from this here, we get v as 2.0 meters per second. Impulse experienced by B during the collision. Impulse is the change in momentum. We are doing this for B, so final minus initial momentum of B. For B, if you see above, it didn't have any initial momentum. So it's just the final momentum. I already have the velocity. I would just multiply by the mass of B. So I would say this is 1.2 times 2 minus 0. Is it 1.2? Yeah, it's 1.2. So this turns out to be 2.4. Again, the same units as momentum, kg meters per second. Suggests why total kinetic energy is less after the collision than the kinetic energy of A before the collision. So you can say energy is lost as thermal energy in the collision. Or you can also say sound, but thermal is usually what the examiner is going for. Next, a footballer kicks a ball vertically upwards. Initially the ball is stationary. His boot is in contact. For this time, average resultant force is given. Ball leaves his foot at 20 meters per second. Find the impulse. Impulse of the force is F delta T. So force is 180. Time for which it acts is 0.05. And using this, you find the change in momentum, which turns out to be 9. So 9.0 kg meters per second. Mass of the ball. So what else do we know? We know that initially the ball was stationary, so it has no initial momentum. So the impulse is basically Pf minus Pi, with Pi being 0 because it does not have any initial momentum, which I just found out as 9, and this is equal to mv, mass times its velocity, which is 20. So then you can just find out the mass, which I'm pretty sure is 0.45 kg. The height to which the ball rises, ignore air resistance. To find the max height, we would use this idea that all of its initial kinetic energy, because it was moving, turns into gravitational potential energy. So I would say this, that the gain in EP equals the loss in kinetic energy, mgh equals half mv square. I would usually write v minus u square for the change in kinetic energy, but I know finally it's not going to have any kinetic energy, because at the max height it would come to rest. And a simple proof by contradiction is this, that if it didn't come to rest, it would have gone a bit further, but if it's not going a bit further, then it's the max height. So masses also cancel out, so the height would be v square over 2g, right? So this is that loss in kinetic energy, which is basically the initial kinetic energy. So the speed was 20 squared over 2 times 9.8. So 20 square over 2 times 9.8 turns out to be 20.4 meters. When the boot is in contact with the ball is no longer spherical. You know this is elastic, or the examiner also accepts strain energy. So elastic or elastic potential is always better to say, but yeah, this is what it is. On to the last question now. 2.1 shows a dummy of mass 70 kg used in a crash test to investigate safety. Car approaches a solid barrier, crashes into the barrier and stops suddenly. Calculate momentum of the dummy before the crash. So momentum is just mv, so mass is 70. It's going to have the same speed as the car itself, which is 1400 Newton second. Determine the impulse that must be applied to bring it to rest. Impulse is pf minus pi. So initially it has some momentum, finally it has no momentum. So it's the same as the initial momentum. That's why this one was for just 1 mark, because it's super easy to identify. In the crash test, the passenger compartment comes to rest, and this time find the deceleration of the passenger compartment. So for the deceleration, I would use the formula for acceleration. It comes to rest. Initial velocity was 20 divided by the time, which is 0.2. This turns out to be 100 meters per second square. Obviously no need to write the minus sign, because the examiner knows this would be negative. That's why he said deceleration. The seat belt and airbag bring the dummy to rest so that it does not hit the windscreen. The dummy has an average deceleration of 80 meters per second square. Calculate the average resultant force applied to the dummy. Very easy, F equals ma. Mass of the dummy was 70. Acceleration, or the deceleration in this case, is 80. So this is going to be 5600 newtons as the resultant force. Last part, deceleration of the dummy is less than the deceleration of the passenger compartment. Explain why this is of benefit for the safety of a passenger. So now when we were doing the theory, we talked about the idea of crumple zones, seat belts, airbags, for why it's good for passenger safety. And we know that the idea in that case was this, that the greater the time, the lesser would be the force acting on the passenger. Now this is also pretty similar. It's just that now the examiner is not talking about the time, rather he's talking about decelerations. So you just need to be a bit broad-minded to answer this question. So we know that as we used in this in the formula above as well, force, mass times the acceleration or the deceleration gives the resultant force. So if the deceleration of the dummy is less than the deceleration of the passenger compartment, this means that the force on the dummy is obviously also less. So what this means is that it would not necessarily hit the seat belt or the airbag in order to come to rest, and hence he is less likely to be injured. That's what I'll say here, is force on dummy is less compared to with the airbag. So injuries are less likely. So that's all the structured questions from my book worksheet as well on momentum. So hope you guys now feel more confident going into your exam with momentum questions. So thanks for your time guys, and see you in the next one.